All right, let's talk about circles. How do we describe and analyze motions along circular paths? We're going to describe circular motion in terms of radius, linear speed, period frequency, and angular frequency, or angular speed. Define uniform circular motion and explain why an object is moving with a constant speed in a circle, and it requires acceleration. Oddly worded. Relate centripetal net force and centripetal acceleration to the quantities that describe the circular motion. Use Newton's second law and free body diagrams to write equations relating centripetal forces to centripetal acceleration. And use centripetal net force and centripetal acceleration concepts to make predictions. A lot of vocabulary this time, so make sure you get this down. We're just going to list the new terms here: uniform circular motion, period, frequency, arc length, arc angle, linear speed, angular speed, also called angular frequency, centripetal acceleration, which is also called radial acceleration, centripetal force, which is also called radial force, centripetal net force. Describing circular motion, the quantities that describe circular motion. Any motion along any part of a circle is called circular motion. It's nice that it makes sense, right? An object does not have to make a complete circle for the motion to count as circular motion. Any motion along any part of the circle will be circular motion. So even if it's just a small little piece, in geometry class you called it an arc length. That's still circular motion, even if you're moving just from here to here, here to there. Just a small little piece. There's several quantities we're going to need to describe circular motion. The timing of circular motion can be described by two complementary numbers, period and frequency. Period is how much time it takes, or would take, for the object to complete one entire circle. So the time it takes to go all the way around is called the period. Symbol that we're going to use is capital T. The units are seconds. Frequency is how many circles or parts of a circle an object completes or would complete in 1 second. So period is the time that it takes to go all the way around the circle exactly one time. And the frequency is how many times it goes around in 1 second. The symbol is lowercase f. The units are circles per second, which has a special name, hertz, with a capital H and a lowercase z, hertz. Period and frequency are reciprocals, so t equals the inverse of f and f equals the inverse of t. On the equation sheet, that's what it's going to show you. An object does not have to complete a full circle for there to be a period and frequency. If a full circle is not completed, we use the number of circles the object would have made and or the number of seconds the object would have taken. The green object completes its circle every 1/5 of a second, or 0.2 seconds. So its period is 0.2 seconds. It completes 5 circles every second, so its frequency is 5 hertz. Blue object, cyan object, completes its circle every 1/4 of a second, 0.25 seconds, so its period is t equals 0.25 seconds. It completes 4 circles every second, so its frequency is 4 hertz. Pink object completes its circle every 1/2 of a second, so its period is 0.5 seconds, and it completes 2 circles every second, so its frequency is 2 hertz. The blue object completes its circle every second, so its period is 1 second, and completes 1 circle every second, so its frequency is 1 hertz. The white object completes its circle every 2 seconds, so its period is t equals 2 seconds, and completes 1/2 a circle every second, so its frequency is 1/2 hertz. Meanwhile, the yellow, every 5 seconds, period is t equals 5 seconds, and there is 1/5 of a circle every second, so its frequency is 0.2 hertz. The red object completes its circle every 10 of a second, so its period is t equals 10 seconds. It completes 1/10 of a circle every second, so its frequency is 0.1 hertz. Radius of a curve. Every circle has a radius. Symbol, lowercase r, or capital R, depending on the situation and the given problem. Units, we will use meters for radius. If the object does not complete a full circle, we can define a best fit circle to the curved path and define a radius of curvature to the curved path. The car in the picture makes a left turn, which is only a quarter of a circle. But we can define the best fit circle in yellow that best fits the path of the turn. The yellow best fit circle has a radius capital R, so this is the radius of the turn. So when I take away that yellow, hopefully you can see that, hey, that's part of a circle. This is not a full circle, but we can still figure out the frequency and period. If the car takes 2.5 seconds to complete its turn, because the car travels only a quarter of the circle in 2.5 seconds, the period would be 10 seconds, because there are 4 quarters in a full circle. So we would take that 2.5 seconds times 4. The frequency is therefore 0.1 hertz, because the car traveled 1/10 of a circle every second. So we can show this with the equation. T equals 1 over F. And therefore F equals 1 over T. Maybe. There we go. So if the period is 10 seconds, then our frequency 1 over 10. Now let's say the car is going ridiculously fast, so it completes a quarter circle in 0.01 seconds, somehow without crashing, sliding off the road and exploding and all of that. Then the full period would be 0.04 seconds, the time the car would have taken to make a complete circle. The reciprocal of that period is 25 hertz, which would be the frequency. This says that if the car were making full circles and the car were allowed to make those circles for more than 1 second, then the car would have made 25 circles every second.